All right, so this will be over the exam number 2 review. So this is on the course website. And let's see, for this exam, you'll have integration by parts, partial fraction decomposition, trig integrals, trig sub, and improper integrals. So that's 7.1 through 7.8 in your book, but we're omitting 7.7 on numerical integration. And I won't cover that problem on the review either. So I'm going to do every problem on the review in order, starting with 1A, and we'll go all the way through problem 6. So let's look at 1A. And I'm going to kind of just go over the solutions fast. For the sake of time, I'm just going to put the solution down. And if you need to pause and go back and stuff, of course, you'll be able to in the video. But we have the indefinite integral of a over x squared minus bx dx. So I'm going to use partial fractions. So let's split this up with our linear factors. So this will be the integral of a over, just take an x out, x minus b. So we'll have integral of a over x plus b over x minus b dx, our linear factors, right? All right, now we will solve for our coefficients. So we'll set up little a is big A times x minus b plus big B times x. So we can expand this a little bit. We'll have a plus b all times x minus ab. This is a nice little factorization. And we can solve for our coefficients. So if I let like x equals 0, so we'll have a plus b equals 0. And so what, negative ab is a. So a is just negative little a over little b. And then big B would be, let's see here, just little a over b, positive. Of course, here assuming that b isn't equal to 0. So now let's set up our integral again. So we'll have the integral of negative a over b times 1 over x plus little a over b times 1 over x minus b dx. So we can integrate all these terms. So I see 2 logarithms. So I'm going to pull out an a over b constant term. And we'll have natural log absolute value of x minus b. And then just minus natural log of x. Right. ln x minus b. I'm just going to reorder them. And plus c. And you could leave it like this if you want. Or you could, of course, rewrite this in quotient form and rewrite it like ln of x minus b over x, if you'd like. But either way, that's the solution to that problem. Okay, moving on. Problem B is integral x cubed minus 2x squared. So let's set this up. Integral x cubed minus 2x squared minus 4 all over x cubed minus 2x squared dx. Okay, so let's just split this up a little bit. So I have an x cubed minus 2x squared and an x cubed minus 2x squared here, so I want to leverage that. So let's write this as the integral of x cubed in parentheses minus 2x squared minus 4 over, and I'm going to factor this denominator, so I'm just going to take out an x squared term. So x squared times x, and then this is just minus 2 dx. So I can lose these terms to get a 1. So we'll have integral of 1 minus, and then we'll have 4 in the numerator, and then our denominator, x squared, x minus 2 dx. And you can, of course, check if you went back the other way. If we had to find a common denominator, we'd multiply this one term by this, and we just end up with this back again, minus 4. Okay. So let's split this up now too a little bit. We want to now apply partial fractions specifically on this term. We're just going to ignore the 4 though, so we'll consider it like 4 times 1 over x squared times x minus 2. So 1 over x squared x minus 2. How do we split this up? We'll have 1 over 4 times x minus 2. And I believe 1 over 4x. Yes, and then minus 1 over 2x squared. And so this is just splitting our common denominators up, right? If we look at 4x here and 2x squared and we multiply by our common denominators, we'd have the same numerator, and then we'd end up with this whole term here. So let's take this now. So I want to say, we're looking back at this, right? We just simplified this. So we'll have 1 minus 4 times 1 over 4 times x minus 2 minus 1 over 4x minus 1 over 2x squared. This is the same as 1 plus 1 over x minus 1 over x minus 2 plus 2 over x squared. We just get this by opening up these parentheses, right? Just multiplying through. Okay. So from here, I think we're really done. We could just go in and integrate all these terms with respect to x. So we'd end up with integral of 1, or dx is just x. This 1 over x is going to give us ln x, or ln absolute value x to be specific. Then this is going to give us ln absolute value x minus 2 minus 2 over x. Remember that the derivative of 1 over x is negative 1 over x squared. And then plus c. And this is our solution. So the only step really on this is this partial fraction step. But I didn't use partial fractions initially. I leveraged this fact to just simplify it a little bit first. And then we applied partial fractions on this inside part specifically right here. Okay. And yeah. And if, oh, and I guess we'd assume that x isn't 0 or 2, but that's not really our problem. All right. Let's look at problem C. So this is the integral of sine squared of 3x dx. And again, these integrals aren't in a specific order at all. So, you know, like this integral is pretty simple to solve, but then some of the other ones are really difficult. It's just a mix of all of them. So don't feel like they should be getting progressively more difficult or something. Okay, so how do I want to solve this? So let's just recall that sine squared of u is just 1/2 1 minus cosine squared of u. And in this case, our u would be 3x. So what do we have? Sine squared of 3x is just going to be 1/2 1 minus cosine. Oh, sorry. Maybe it's specific. I messed up here. This isn't cosine squared, right? This is cosine of 2u. Okay. So cosine of 2 times u is going to be 6x, so we'll have cosine of 6x. Now this is super nice to integrate, so we'll have the integral of 1 minus cosine 6x over 2 dx. This is just going to give us x over 2 minus 1/2 integral of cosine of 6x. You could just make a u sub here, but we'd get, let u equal 6x. We'd have x over 2 minus, we're going to divide by this 6, so 1/2 times 6, so minus 1 over 12 sine of 6x plus c. So this is our solution. Very simple, just use this identity. All right, oops. Now we have integral d. Let's see. This is a pretty good one. So we have the integral of 1 over 9 minus x squared dx. So let's do partial fractions on this. So I'm going to split this denominator up. So we'll have 1 all over, let's see what these factors are, just 3 minus x and 3 plus x. dx. All right, now we have linear factors, so we can set up our partial fractions. This will be big A over 3 minus x plus big B over 3 plus x dx. And that's our partial fraction step. So we can solve for this, setting it equal to 1. So 1 equals A times 3 plus x plus B 3 minus x. So like x equals negative 3, x equals positive 3. So A minus B is 0. 3 times A plus B is 1. So A is 1/6. And that's the same thing as B. So A equals B equals 1/6. So now let's set up our integral again. So we'd have integral, let's pull this 1/6 out. So then our coefficients are just 1. So 1 over 3 minus x dx plus integral of 1 over 3 plus x dx. So we're going to get some logarithms. So 1/6, I don't know, times negative natural log of, this will give us 3 minus x plus ln 3 plus x plus c. And that's it. That's our solution. Pretty simple. This has a really nice, just easy factorization. So we're able to get these really simple linear factors that are easy to calculate. Okay, let's look at integral E, part E. So this is the integral of square root x squared minus 9 over x dx. Okay, so this is going to be a trig sub, right? Anytime we see square roots and we see something, in this case in the form of x squared minus a squared, we are going to use a trig sub. The one that we're going to use in this case is the form for x squared minus a squared, so that'll be a secant substitution. So we'll let x be a secant theta. A here should be 3, of course, because the square root of 9 is 3. So x equals 3 secant theta. Our dx is just 3 secant theta tan theta d theta. Nice. Okay, so let's look at what the integrand becomes. So we'd have, well, let's look at the root first, right? So x squared minus 9 equals we let x be 3 secant theta squared, so 9 secant squared theta minus 9. Now, what I'm going to use here is the tangent identity. So this will be equal to 9 tan squared theta square root, which just comes out to 3 tan theta. All right, so now our integral, our numerator becomes 3 tan theta. Our denominator is just x, which we let be 3 secant theta. So over 3 secant theta times our dx, which is 3 secant theta, tangent theta d theta. Look at this. This is super nice. We can get rid of these. So we have a tangent and a tangent. So we have 3 tan squared theta d theta. So now we're looking at this integral. So we used this identity in here to get to tangent. Now I'm going to go the opposite direction to get to secant identity. So we can write this as, we'll take the 3 out of the integral. And this is equivalent to secant squared theta minus 1 in parentheses d theta. Now, this is just 3 times, I know the derivative of tangent is secant squared theta. So we'll have 3 times tan theta minus integral of d theta is just theta plus c. And then now all we have to do is find out what our theta is. So x equals 3 secant theta, which means secant theta, right, we divide by 3. Secant theta is x over 3. So theta is arc secant of x over 3. Okay, so that's it. That's our theta. So this means our solution is going to be, let's see, we'll have root x squared minus 9 minus 3 arc secant of x over 3 plus c. And that's our solution. And equivalently, if you remember that secant is 1 over cosine, then arc secant can actually, you could make this arc cosine if you'd like. And all that would happen is we flip the inputs. So x over 3 becomes 3 over x. Not necessary, of course, but it's there if you want to use it. Okay, let's move on to integral f. So where is this at? Oh, here we go. Okay, so we have 1 over, why can't I pull this up? Okay. Integral of 1 over 2t squared plus 3t plus 1 dt. Okay, let's do partial fractions on this. So this denominator actually factors really nice. So 2t squared plus 3t plus 1 is just the same as 2t plus 1 times t plus 1. Now we have linear factors, so we'll set it up as 1 over 2t plus 1 times t plus 1 equals a over 2t plus 1 plus b over t plus 1. So now we'll solve 1 equals a times t plus 1 plus b times 2t plus 1. So this is, I could rewrite this as, we'd have a plus 2b, I'll share a t factor, and then just a and b, so a plus b. Okay, t equals 0. So let's look at, we'll have a plus 2b equals 0. A plus b equals 1. So this will give us b equals -1. And a will just be 2. Okay. So now we'll have the integral of 2 over 2t plus 1. And I'm just going to flip the order just for the sign. So I'm going to do my b coefficient first. So integral of 2 over 2t plus 1 minus 1 over t plus 1 dt. Okay, so we have a 2 in the numerator and a 2 in the bottom. So when I pull that 1/2 out, it'll cancel with the 2. So we'll have 2 over 2, so it'll just be natural log absolute value of 2t plus 1 minus ln of t plus 1 plus c, and that's the answer. So I factored the denominator, and then I performed partial fractions on it. And we just looked at linear factors here. All right, let's look at integral g now. So this is the integral of x cubed plus 4 over x squared plus 4 dx. So this is kind of a strange one. So what we want to do on this is perform long division on this polynomial so that we can get it into a form that's nice to integrate. So it's been a minute since I've done this, but let's do this. So we'll set up, okay, so we want to match the leading terms of the dividend and then multiply back, do a back sub and subtract. So we want to form a general third degree polynomial with our polynomial. So we have x cubed plus, we don't have an x squared term, so this would be 0x squared. We don't have an x term, so this would be plus 0x plus 4. And then this would be over x squared plus, we don't have an x term, so 0x plus 4. Okay, the leading term of our dividend, our numerator, is x cubed, and the leading term of our divisor is x squared. So we're going to have a ratio x cubed to x squared is just going to be x. So x cubed, x squared just gives us x. So we'll multiply the whole divisor by x. That's the next step. So we'll have x times x squared plus 0x. And our divisor is our numerator, by the way. So x times x squared plus 0x plus 4. This will just be x cubed plus 0x squared plus 4x. And then we'll subtract from the current dividend. So we'll have x cubed plus 0x squared plus 0x plus 4 minus x cubed plus 0x squared plus 4x plus 0 we can write. So what do we get here? Negative 4x and then just a 4. So this is actually our remainder. So like I can call this r. So the stop condition for polynomial division is that the reminder's degree is less than the divisor's degree. So the degree of our remainder here is 1, right? Degree 1 for x, which is less than 2, which is the highest degree of our divisor here, 2. So we can actually stop. So how do we put everything back together? Okay, so our quotient, so this is what we can call our quotient, Q. This is the ratio of our highest term to our divisor to our dividend. So we'll take x times x squared plus 4 plus minus 4x plus 4, and we'd get back what we had originally. So what I want to do now is just set up our integral. So we'll have the integral of just x dx plus the integral of minus 4x over x squared plus 4 dx plus the integral of positive 4 over x squared plus 4 dx. So what this looks like is that we split up x cubed plus 4 and over x squared plus 4 into some quotient, which in this case we found to be x, plus a new fraction which just has the remainder, which is minus 4x plus 4 over x squared plus 4. And that's what we've set up here to integrate. So now that we're looking at just these terms, these are not too difficult to integrate. So let's just look at the first one. So the integral of x dx is just going to be x squared over 2 plus c. Easy. The integral of minus 4x over x squared plus 4. I'm just going to make a u sub. We can solve this using a u sub. So we'll let u be x squared plus 4, right? Because I want its derivative to be equal to x, so I can collect this x that's in the numerator. So my du is just 2x dx. And this also implies minus 4x dx is negative 2 du, right? But what happens when we plug it in? That x gets collected, so we'd have the integral of negative 2 all over our, this whole thing was a u sub du. So this would just be negative 2 ln absolute value of u, negative 2 ln absolute value of x squared plus 4. Okay. And then now let's look at this last integral. So the integral of 4 over x squared plus 4 dx. This is actually really nice. We just have an arctangent form. So recall that, you know, the integral of 1 over x squared plus a squared dx is 1 over a arctan of x over a. So this will be 4 times 1 over 2 tan inverse of x over 2. This can be simplified just 2 tan inverse x over 2. So putting it all together, we'll have x squared over 2 minus 2 ln absolute value of x squared plus 4 plus 2 tan inverse x over 2 plus c. And this is our solution. So nothing too crazy, just some polynomial division and then just putting it all together. So if you need a refresh on polynomial division, then I would recommend doing that. Okay, let's look at the integral of, what is this, letter h now? So h 1 over 16 plus t squared dt. Super simple. This is an arctan integral. We're going to use the same formula we just used. So this will be 1/4 tan inverse of t over 4 plus c. Right, just remember this. That's the integral of dx over x squared plus a squared is 1 over a tan inverse x over a. Okay, now we'll be on integral number I. So this is letter I. This is the integral of 1 over 1 plus 2r dr. Let's just make a u sub. Get u be 1 plus 2r. So du is just 2dr. So dr is 1/2 du. So we get integral of 1 over u times 1/2 du. So this will be 1/2 ln absolute value of u, which is equal to 1/2 ln absolute value of 1 plus 2r plus c. And that's our answer. Just a nice u substitution. Okay, now we're on letter J. So J is the integral sine cubed theta cosine squared theta d theta. Okay, this isn't going to be a trig sub. We're just going to use trigonometric identities. So what I want to recognize, I have an odd power of sine and even power of cosine. So we're going to save a power of sine and let my u be cosine. So let's do this. So this will be integral of sine squared theta sine theta cosine squared theta d theta. And this is integral of 1 minus cosine squared theta times sine theta cosine squared theta d theta. Now we can make a u sub. So again, we'll let our u be cosine theta because of odd power of sine. So our du is negative sine theta d theta. This sine theta gets collected here. So we'll have, pull out a -1, integral of 1 minus u squared times u squared du. Open our parentheses a little bit. We'll have u squared minus u to the 4th. So this is just negative u cubed over 3, and then plus u to the 5th over 5. And I distributed this negative, if you couldn't tell. Plus c, this is really equal to negative cosine cubed theta over 3 plus cosine to the 5th theta over 5 plus c. And this is the solution to our integral. Pretty simple, just recognize odd power of sine, means we manipulate sine and then let our u sub be cosine, and we use this reduction formula here. Okay, so that's letter J, so we're on to K now. Surely they could have just used numbers at some point, but K will be the integral from x to the 5th ln of x dx. Let's do some integration by parts. So my u to be ln x. So my du is 1 over x dx. My dv is going to be x to the 5th dx. And my v, after I integrate, is going to be x to the 6th over 6. Now we'll use our integration by parts formula, uv minus integral v du. So this will give us x to the 6th over 6 times the natural log of x minus the integral of v du is x to the 6th over 6 times 1 over x dx. You can get rid of an x here. So we have x to the 6 over 6 minus integral of, we'll pull out a 1/6. So we'll pull out a 1/6 here. And then just the integral of x to the 5th dx. So this is x to the 6 over 6 So this will be integral of x to the fifth will be x6 over 6. So this will be x to the sixth over negative 1/6 times 6 will be 36. So over 36 plus c. And this is a solution to our integral. So just standard integration by parts. Pick u to be ln of x. Always, usually, in these integration by parts problems involve the natural logarithm. Because you don't want your dv to be ln of x dx, because then they're expecting you to know how to integrate ln of x. But trial and error, I guess. Okay, so that was k, so now we're on L. So L. So this is the definite integral evaluated from 2 over square root of 3 to 2 times the square root of 3 of x cubed over square root x squared plus 4 dx. Okay, so let's do some u sub. So we'll let our u be x cubed plus 4. Right. So we'll have u is x squared plus 4, or sorry, we'll let our u be x squared plus 4, not x cubed. So our du is just 2x dx. Equivalently, our term up here in the numerator, x cubed dx, we can simplify this a little bit. This is equivalent to just saying x squared times x times dx. All right, this will be a little helpful. And the manipulation we're going to do is that our u was x squared plus 4. So this x squared here is going to be u minus 4, right, from this. This would be u equals, or sorry, this would be x squared equals u minus 4. So we'll have u minus 4 times 1/2 du. So our integral now is going to be, we'll just look at, we won't look at the balance just yet. We'll have u minus 4 times 1/2 in the numerator. That's what we just simplified. Over, this whole thing was our u, so square root of u du. Let's pull out this 1/2. So this is equivalent to writing, let's see, u to the 1/2, square root of u, minus 4, bring that square root up to the numerator, u to the minus 1/2 du. Okay. Now let's just integrate this straight through. So we'll have 1/2, 2/3, and I haven't forgot about the bounds yet. I'll get to it in a second. So 1/2, 2/3 u to the 3/2 of the cube root minus 8 u to the 1/2 plus c, because we don't need it, whatever. Okay. So this is, so our valid antiderivative would be then 1/3 x squared plus 4 to the 3/2 minus 4 x squared plus 4 to the 1/2. We can simplify this a little bit. So 1/2 or 1/3, just the square, square root x squared plus 4, and then we'd have, let's see, 4 times 2, so an x squared minus 8 out here. But, of course, these are equivalent. Okay, so let's look at our endpoints. So when a equals 2 divided by square root of 3, a squared is equivalent to 4 over 3. So a squared plus 4 square roots would be 4 over square root 3 So if our integral has solution antiderivative evaluated at b minus antiderivative evaluated at a, this would be our f of a, which would be 1/3 times 4 over root 3 times 4 cubed minus 8. So f of a is something not fun. So negative 80 over, I think, 9 square root 3. Yes. Okay, now we'll look at b. So b equals 2 times square root of 3. So b squared just equals 12. Square root of b squared plus 4 equals just 4, right? So now this will be our f of b, our upper bound. So this will be 1/3 times 4 times 12 minus 8, which is 4. So that gives us 16 over 3. So our solution then is 16 over 3 minus 80 over 9 square root of 3. So that becomes plus 80 over 9 square root of 3. And you can find a common denominator if you'd like. I'm just going to leave it like this. And this is our solution. So nothing too crazy. We're just making a u sub. But this is an example where we have to do like a little bit of manipulation to get a good u sub. Okay, so that was L. So now we're going to look at M. M, integral from 0 to a of x squared times the square root of a squared minus x squared. Okay, so this is screaming trig substitution. It literally gives us a squared minus x squared, so that's going to be, so our substitution is going to be x equals a sine theta, right? We don't have a value for a in this case, so we're solving like a general case. So dx is just going to be a cosine theta d theta. D theta. So then our square root in here, a squared minus x squared equals a squared sine squared theta. Oh no, sorry. So this will just be a squared minus x squared will be a squared sine squared theta. This is equivalent to a squared cosine squared theta. So then the square root just gives us a cosine theta. All right. And let's look at our bounds. So we're going initially from x equals 0 to x equals a. Now we're going to go in terms of theta. So when x equals 0, this means x equals a sine theta, divide by a on both sides. Sine theta equals x over a. So theta is sine inverse of x over a. When x equals 0, this is just sine inverse of 0, which is just 0. So our lower bound is theta equals 0. When x equals a, we have that theta is sine inverse of x over a, but x equals a, so it's a over a, which is just sine inverse of 1, which is just pi over 2. So we're going from theta equals 0 to theta equals pi over 2. All right, so those are our new bounds. So this x squared term in the front is a squared sine squared theta. It's the square of our substitution. The square root became a cosine theta. And then we have our dx, which is a cosine theta d theta. Okay, so I want to pull out an a factor. So we'd have a squared times a. So that's a to the fourth. So we'll pull out an a to the fourth. integral 0 to pi over 2. Then this will just be sine squared theta and cosine times cosine squared theta. D theta. We have an identity for this. A to the fourth, 0 to pi over 2. So this will become 1/4 sine squared of 2 theta, d theta. And now we can use another reduction to turn sine squared into terms of cosine. So we'll have, this will be a to the 4 times 1 over 4. So a to the 4 over 4, 0 to pi over 2. This will become 1 minus cosine of 2 theta all over 2. Right, this is our reduction formula. Sorry, this will be, this has to be a 4 theta. Because it's double what's on the inside. Over 2 d theta. So, let's see what this gives us. When I integrate this 1/2 is going to come out. So we'll have a to the 4th over 8 times this integral of d theta is going to become theta minus 1/4 sine 4 theta evaluated from 0 to pi over 2. So this is equal to a to the 4th over 8. Pi over 2, that's going to go to 0, so just times pi over 2. So this could be written pi a to the 4th over 16. And this is our solution. So just a nice trig sub on this general case. All right, so that was M, so let's do N. Letter N, integral 0 to t minus s squared ds. So let me expand this a little bit. So t minus s squared is just t squared minus 2ts plus s squared. So this whole integral then just becomes integrating these factors. So we'd integrate all of these with respect to s, and we'd end up with t cubed minus t cubed. I guess let's be specific. We'll have t squared s minus ts squared plus s cubed over 3 from 0 to t. So this is t cubed minus t cubed plus t cubed over 3. These go away, so our solution is just t cubed over 3, or 1/3 t cubed. So this is nothing special about this integral. We just expand it and algebrate these using power rule. Okay, let's look at the integral letter O. So this is the integral from 0 to pi over 2 cosine x 1 plus sine squared x dx. Okay, this isn't too bad. We're going to let our u be sine of x. du is cosine x dx. So we can collect one of those cosines. And let's change our bounds. So when x equals 0, this means that u equals sine of 0, which is 0. When x equals pi over 2, this means that u equals sine of pi over 2, which is just 1. So we're going from 0 to 1. So integral from 0 to 1 of this cosine gets collected, so we have 1 over 1 plus u squared du. And now we've turned this into an arctangent, so this will just be tan inverse of u evaluated from 0 to 1, because we already changed our bounds. So this is tan inverse of 1 minus tan inverse of 0, which is, so minus tan inverse of 0, and this will just be pi over 4. All right. Now we'll do letter P. P. Integral from 1 to 2 of x plus 1 squared over x dx. So I'm just going to expand this numerator. So this will be equivalent to the integral from 1 to 2 of x squared plus 2x plus 1 all over x dx. And now we can integrate these individually. So we'd have the integral of x squared over x dx plus the integral of 2x over x dx plus the integral of 1 over x dx. And we just end up with 7/2 plus natural log of 2 when we plug everything into the end. This, of course, just becomes, this becomes x, this becomes 2, and then this becomes natural logarithm. Okay, let's do Q now. So Q is, it's like the inverse of P, right? We're just flipping the numerator and denominator, but it does change our solution. So we'll have the integral from 1 to 2 of x over x plus 1 squared dx. And this is how I want to expand this. So I want to rewrite this as the following: x plus 1 minus 1 over x plus 1 squared. All right, these two are equivalent because these ones go away and we're just left with this copy of x. But doing this allows us to split this up easier, or at least makes it more visible. So this will be 1 over x plus 1 minus 1 over x plus 1 squared. And we can see if we took our common denominator, we'd get back to this. So all I'm going to do now is just integrate these. So I'm going to integrate this all with respect to x. So 1 over x plus 1 is just going to give us, natural log absolute value of x plus 1 plus this whole thing when solved with like a u sub, it just gives us 1 over x plus 1. Derivative of 1 over x, negative 1 over x squared. So plus c is our solution. And, we are evaluating from c. So let's just evaluate this from 1 to 2. So 1 to 2 will give us ln, let's see, ln 3 plus 1/3 minus ln of 2 plus 1/2. We could write it like that, or I think we could do ln 3/2 minus 1/6. And this is your solution. So pretty simple, nothing too crazy. Let's do now the last one on this part, which is letter R. So this is the integral from 0 to 1 of e to the x over 1 plus e to the 2x dx. So let's just let u be e to the x. du is e to the x dx. Now I can collect that ex in the numerator. And let's change our bounds. So we're going from x to u. So when x equals 0, this means u equals e to the 0, which is just 1. When x equals 1, this means u equals e to the 1, which is just e. So now we're integrating from 1 to e of 1 over 1 plus u squared du. This is just inverse tan of u evaluated from 1 to e, since we already changed our bounds. So this gives us tan inverse of e minus tan inverse of 1, which is pi over 4. So tan inverse of e minus pi over 4. And that is it for these first integrals on this page. And then I'll go over all the improper integral stuff now.